In this video, we are going to drive these all three profiles using analytical techniques. So start with the first problem, that is the laminar flow in a circular pipe. And here the first case is the laminar flow in a pipe. And so just let me draw the pipe here. So the heading is that the velocity profile in pipe. This is a laminar flow case. For turbulent case flow, the velocity profile is different. Okay, and also because it's a pipe flow, so instead of solving them in 3D, so in 3D this will require XYZ. So this will be more difficult if you solve this case in the XYZ because we have the three coordinates. So three variables, and if we transform them into theta, angular, radial, and axial. So instead of Z, we are using X for the axial here. So we can transform them into the radial coordinate system, our polar coordinate system. So basically, you know that the tan theta is equal to y by x and r square is equal to x square plus y square, and z will be same as the axial direction. Okay, so in this case, if there's no variation of the flow in angular direction, which is always the case, mostly the case, so instead of having three variables, we can have that only two variables. Okay, so it means that now we can be able to solve the problem in two coordinates. So this will reduce our equations greatly. So that's why I'm going to draw the axis here. Okay, and the velocity profile is parabolic in nature. We will confirm this thing after derivation. So we have the velocity at this location, and this is following the parabolic velocity profile. So this is very rough figure I have drawn here. So actual figure is symmetric around the axis. Axis also drawn a little bit on the lower side. So anyhow, and so here what we are going to place is the axial coordinate and the radial coordinate r. And also we are going to take the one section here. So this one section, because it's from pipe, so for the one section this will be a ring. So ring having thickness equal to dr and radius is equal to r. So here we have this portion is a dr and this portion is in the axial direction, which is equal to dx. Okay, so because the area for the pressure which is being applied here will be normal to the face, so that's why I will draw the important forces on this particular element. And these forces are the pressure forces normal to the element. This is the P at the x location. And this is the dx. So the second force here is equal to px plus dx. Also we can write down this px plus dx. Also we can write down this thing. This is equivalent to the px plus d by dx, px into dx. Okay, so because this will be shear stress is applied parallel to the geometry, so area would be considered over this one. So this area, you can see this area would be equal to the dx, and the circumference of that particular geometry is a 2 pi r. So therefore the area here would be equal to, so we can say this is the area for shear stress. So the area for the pressure will be equal to, it's a 2 pi r, that is circumference, 2 pi r into dr. And here we have the shear stress, and this direction is like this. And on the top side, the shear stress would be like this. So this is the tau xy, and this is the, so we can write down this tau plus tau and x plus dx. Okay, x plus dx. So this is again, so we can write down this tau x plus dx. This is equal to, this is the tau x plus dx is equal to basically the tau x, y, or tau only, plus d by dr into tau into dr. Okay, so this will be like this, and the area for this section, this shear stress would be equal to 2 pi r dr, 2 pi r into dr. Okay, there is the slight correction, so let me explain this thing. The area here would be not 2 pi r dr, but you can see that for the axial location, the area would be equal to the, we're talking about the 3D, so this will be equal to the one ring, and this one ring is extending like this. Okay, so this ring has the circumference of 2 pi r, and this length of small element is dx. Okay, so for shear stress, this is equal to 2 pi r into dx. Okay, but for the pressure, this area, this is area for shear stress, this is the area for pressure, this is equal to 2 pi r into dr. If you open this whole strip, this will be like dr, and here this is equal to, this length will be equal to 2 pi r. If you open this ring, so 2 pi r, so this is area will be equal to 2 pi r into dr. Okay, so this thing is clear. Now we have to make the summation of forces, and also before that we go further. So here r is equal to 0, and here r is equal to capital R, that is the radius of this pipe. Okay, and the boundary conditions we can have here are different. So at r is equal to 0, the one thing is that the velocity is maximum, so u is equal to u max, and also the derivative of velocity is 0 here at this point. So du by dr is equal to 0. So at r is equal to 0, the u is maximum, and du by dr is equal to 0. But at r is equal to capital R, u is equal to 0. So we have these boundary conditions. Now I will apply the force summation. So force summation is, so apply the force summation here. And this should be equal to 0. So we have for the pressure force, we have the 2 pi r dr, this is the area, into P, and this is at the location x, and this is in the positive direction. As you can see, this is in the direction of the flow, this is positive, and this pressure is in the opposite direction, this will be negative. This shear stress is negative, this shear stress is positive. So this should be taken in this phase. So any force in the direction of flow is positive. Any force opposite direction of the flow is a negative. So here we have the minus 2 pi r dr. This is a P at x plus dx, and then also we have the minus 2 pi r dx, this is the tau x, plus we have the 2 pi r, so we can write down this thing in the bracket. So this is 2 pi r dx into tau x, 2 pi r dx, this is the tau but at the x plus dx is equal to 0. So now I can divide this whole thing by, so divide by 2 pi dr and dx, and also we'll rearrange this whole thing so we get this thing as, and you can see that this will be like this will be the px this is a px plus dx. Okay, and the minus sign on the here minus px, this because this is minus px will be positive px, and this the positive px will be px plus dx will be negative value. So that's why I taken out the minus sign common from these two terms. And finally we get here dx, because we are dividing by 2 pi, so 2 pi will be cancelled, and the dr will be also cancelled. Dr will also be cancelled, and here we have the ds remaining in the denominator. And similarly we have the positive quantity here. So only thing that will be here inside, because this r will be variable, so that's why this r will be inside the equation here. So but for the pressure, because pressure is not a variable, so that's why, but shear stress is a variable function of r, that's why r will be remain inside the bracket, but the pressure is not a function of the r, that's why this r is taken out to be a common from these two terms. So that's why I will write down this thing as r shear stress at r plus dr minus, so this is the at the r, and this is at the r plus dr. Okay, so minus this will be the r tau r divided by dr is equal to 0. So now we have this thing. So from this, this thing is the derivative, this thing is the differential. So this is the minus r dp by dx plus this is the derivative of shear stress, so d by dr, this is the d by dr, and this is the shear stress, and r is equal to 0. Okay, so now we have this equation, so I can write down this thing as dr tau and by dr is equal to positive r dp by dx. Okay, now we know that shear stress is equal to the dynamic viscosity mu into du by dr. du by dr. So we can write down this thing as this. So now I can write down this thing as d by dr, and r is here, and we have the mu du by dr is equal to r dp by dx. And since this mu is constant, so I take it out, and then I will take it on the other side, on the right side. So this will be the d by dr r du by dr is equal to r upon mu dp by dx. Okay, so now we can integrate this equation, so we will get this derivative will be removed. So we have the r du by dr is equal to this r will be r square upon 2 mu and dp by dx plus c1. Now if we divide this whole thing by the r, so this r will be removed, and this 1 power will be removed from here, and also we get the 1 by r over here. Okay, so I write down this thing in the second step. So this will be the du by dr, and this r square will be now single r, so this r upon 2 mu dp by dx plus 1 upon r c1. Okay, so now if you integrate this thing again, so we get the u as a function of r is equal to this r square upon 2 will be r square upon 4 mu and dp by dx plus 1 upon r will be log of r c1 plus another constant which is c2. And the boundary conditions we have is that the u is equal to 0 at r is equal to r. And also we have the boundary condition that du by dr is equal to 0 at r is equal to 0. So now we have the two equations. The main equation is this one, and the one is over here. So basically we'll apply the boundary conditions here and also here. Do not apply the boundary condition because it's a 1 upon r, and this will be a some unknown undetermined number. So we apply the first this boundary condition on at u is equal to 0, r is equal to r. And second boundary condition is that du by dr is equal to 0 at r is equal to 0. So this term will be 0. This term also will be equal to 0. So it means that the C1 is equal to 0. So this term will be now removed from here. So you will apply second boundary condition is that the u is equal to 0. U is equal to 0. So the C1 is 0. So you will apply the u is equal to 0. So this will be 0 is equal to, so at r is equal to r. So r square upon 4 mu dp by dx. And since this is the log of r, but already C1 is 0, therefore this term is 0 and plus C2. So from here you can see that the C2 is equal to minus r square upon 4 mu into dp by dx. So you have to put this term into the equation for the velocity profile. So this will be now we have to insert the C1 and C2 in this equation. And the C1 is also equal to 0. So C1 is equal to 0. So that we get from the very first equation. So you have to put these two constants into the equation and you will get the equation in this way. So we have u is equal to 1 upon 4 mu r square dp by dx minus r square upon 4 mu dp by dx. This is a C2. That's why there is no other variable over here. And if I take out the minus 1 upon 4 mu and r square common and dp by dx also common, so you will see that the positive term will be negative. So this term will be in the second part of the bracket. So this term will be over here. So this will be the minus r square. This term will be positive and r square is taken out, therefore this will be only 1. And since there was no r square, capital R square over here, this will be divided by r square here. So now we have the equation that is a minus r square upon 4 mu dp by dx 1 minus r square upon r square. Now this equation is perfectly okay if we know the value of pressure gradient, which we usually speaking do not know right now. Or in the most cases, we do not know the dp by dx in any pipe. We can find out the dp by dx, but right now we don't know this thing, and usually speaking we don't use the dp by dx in the finding the velocity profile. So basically now we have to change this dp by dx to the known terms, which we can easily specify or easily we can know it. So now we have to do one more thing. You know that the u is equal to u maximum at r is equal to 0. So if you put this value at r0, so this will be 0 and 1 minus 0 will be 1. So 1 into something will be exactly same thing. So this u maximum will be minus r square upon 4 mu dp by dx 1 minus r square upon r square. So now if you compare these two equations, the u equation and the u maximum equation, what do you see here? The u equation is this one and u maximum equation is this one. So if you compare these two equations, you will see this thing that, so this term will be 0 basically. This is when r is 0. Okay. So u maximum will be this term. So if you compare these two equations, you will see one thing. That thing is that this term and this term, they are exactly same. It means that I can write down the u as this term. This term is the u maximum. So I can write down the u is equal to u maximum as a u maximum and 1 minus r square upon r square. So we have changed the unknown values to the known value, but the issue here is that u maximum is not usually speaking known value. So If we take a pipe here, and you will see that the velocity profile will look like this, parabolic velocity profile. Okay, so the U maximum is over here. This is the where R is equal to 0. So this is the U maximum. The issue is that, usually speaking, on the pipe inlet, we are given the velocity inlet, and this is basically a U mean. And U mean, if you take average quantity, this will be somewhere maybe here. So this is a U average or U mean. So because the U mean is a known quantity, so we must change the U maximum, or we must find out the U maximum in terms of U mean. Okay, so that's why now our struggle is to find out the U maximum in terms of U mean. Okay, so now if you take a look here, you know that the flow rate Q will be equal to U average or U mean into area. Okay, so for the full pipe, the area would be equal to, if you take just a simple area. So this simple area would be equal to, for the whole pipe, will be pi r square. But if you take this area for a small element, this dA would be equal to 2 pi r and dr. This is very much clear thing. Okay, so for the complete area, this will be pi r square. This is the r. And for small element, this will be the r and dr. So 2 pi r into dr. So just look at the lecture I explained earlier in this same section. So this is what we have right now. So now I have to determine the value of U maximum in terms of the U mean. Okay, so I can find out the U mean as the equal to Q into A. So but we know that dQ will be equal to U as a function of R into dA. Okay, so I can find out the UR will be equal to, this UR will be equal to now, this UR will be, this is the same as we have shown. So this is a minus R square upon 4 mu and dP by dx, and 1 minus R square upon R square, and the dr is 2 pi r dr. Okay, so if we have to find out the value as for the complete geometry, this is only for the one single ring here that is shown here. If you want to find out the flow rate for the whole pipe, this will be the integration from 0 to r. So this Q for the whole pipe will be the 0 to r, and dq into, so this will be the dq. So this is dq. This is equal to integration from 0 to r minus r square upon 4 mu dP by dx, 1 minus r square upon capital R square, 2 pi r and dr. So let me change my pen color. So now we can see that this thing is over here. So I can take out something common from here. So we have the 2, we can cancel out. This is 2. And the remaining things will be here. So I can take out outside will be the minus r square upon 2 and also pi. Okay, and also dP by dx, and inside integration we have 1 minus r square upon r square and dr. Okay, and you also know that the U average will be equal to, or the U mean will be equal to this Q upon area. So this will be equal to, the Q is given above, so this is minus pi r square upon 2 dP by dx, integration 0 to r, 1 minus r square upon r square into dr, and divided by area. This area is equal to pi r square. So pi cancelled, r square cancelled. So we have the minus, and also there should be the mu. So this mu is inside the this thing. So this mu should be here. So this mu should be taken out also. This is the 2 mu. This is the 2 mu. Here also this is the viscosity. So this term should be here. So finally we get the equation as minus 1 upon 2 mu dp by dx and integration from 0 to r 1 minus r square upon r square into dr. Okay, now just apply integration. So we get that this is equal to minus 1 upon 2 mu dp by dx. This is equal to r. This is equal to r minus, this is equal to r, this is equal to r cube upon r square and also 3. So the limits are 0 to r. So if you simplify this thing, this will be minus 1 upon 2 mu and dp by dx, and here this will be the r minus, so r cube upon r square will be the r, so this will be the r upon 3. This is the 1 minus 1 upon 3. Okay, there is one correction also. There should be the 1 r also here. So this r should be considered here. So this r will be multiplied here. This will be the r here. This is the r and r cube. So this will be the r square upon 2. And this will be the r power 4 upon 4. So if you put the limit, this will be the r square upon 2 and this will be the r square upon 4. So 1 upon 2 minus 1 upon 4 will be equal to 1 upon 4. This is 1 upon 4 r square. So if you take the 1 upon 4 outside, this will be the minus 1 upon 8 mu. And r square will be taken here. This will be the dp by dx. This is the u mean. So now if you compare this thing, you can see that the u maximum was equal to minus r square upon 4 mu. So the u maximum was equal to the u maximum which we derived earlier is equal to minus r square upon 4 mu dp by dx. So if we divide the u maximum by the u mean, so what you get here is that the u maximum upon u mean is equal to minus r square upon 4 mu dp by dx minus r square upon 8 mu, this is the u mean, and dp by dx. This is cancelled, r square cancelled, minus sign cancelled, mu cancelled, and this is cancelled. So this 2 will be now in the numerator. So u maximum upon u mean is equal to 2 times. So u maximum for laminar flow in a pipe is equal to 2 times of u mean. So we can find out the u maximum by this equation, and we know that the u is equal to you know this thing is equal to u maximum into 1 minus r square upon r square, and you can find out the u maximum by this equation, that's equal to 2 times of u average. Okay, so this is the derivation of velocity profile for laminar flow in a pipe. Okay, so now let me show you this complete derivation. So we started from the very beginning, that is over here. Okay, so we have taken the pipe, we drive the equations, and then we found out the areas, and then we made the summation of forces. So finally we integrated the equation twice, and we found out the constant of integrations. So then we find out the u maximum, then we found out the value of u average or u mean value, and then we got the ratio of u maximum to u mean. So from here we can find out the value of u maximum, that is unknown value in the velocity profile. Okay, so I hope that this was very much the detail and it clears your doubts about the velocity profile in a pipe.